right? So we'll talk about a new algorithm called column generation, and it's closely related to something called Dantzig Wolfe Decomposition. Let's motivate this by an application called the cutting stock problem. Right, so imagine there is a paper mill, right? And then the paper mill is producing paper rolls of different width. Right? So you can think about you have a different width of the papers you want to produce with this so-called master reels. Right? The original paper has a fixed length. You can think about this length as maybe 100, right? So these are the length. Each of these paper roll, it is of the same length, maybe 100 inches, right? And for those small paper rolls, they may have, maybe let's just give it some random numbers, 25, 20, 30, and then, let's say 20 again, right? So you want to cut this 100-inch paper roll into those smaller paper rolls, right? And then the customer demand are different numbers of rolls of various size. For example, the customer may need 10 of the 25 inches paper rolls and 10 of the 30 inches paper rolls, right? Then the idea is you want to minimize the number of rolls you cut to satisfy the customer demand, right? So this problem is quite ubiquitous in different industries, right? Think about those, maybe the company that sells clothes, right? You want to sell clothes of different size, maybe small, medium, large, extra large, right? And you have a demand for different size of the clothes, right? And the clothes you use to cut those different sizes, usually they produce at a same length, like let's say 100 inches, and you want to cut from those different sizes from a very large cloth. That's what you are going to solve. And if you have a large, paper reel, you may have some of the material wasted. They are called the trim loss. So let's formulate this problem a little bit using some data, right? So let's say you are given 20 rows of paper, each have width 100 inches, and then you have demands of different width. Let's assume you have demands for three different widths. They are 25 inches, 35, and 40 inches. And the demand of those different widths are 7, 5, and 3. Right? The idea is to say you want to minimize the number of rows you use in order to satisfy the demand of different widths. And for each of the paper roll of 100 inches, there are different ways of cutting them. Right? For example, with 100 inches, you can get 4 rows of 25 inches. Right? It can be divided by 25. And also, you may get 2 rows of width 35 and 1 row of width 25. Then as a result, you still have 5 inches you didn't use, right? So the trim loss here is 5 inches here. And as you can imagine, if you have different types of width, there are different combinations of cutting this paper roll, right? And the idea is that we want to get a cutting plan that we satisfy all the demands and we minimize the number of used rolls to satisfy all the demand, right? Think about a cloth company. You have a forecast of different sizes you need, and then you want to minimize the amount of raw materials you use to satisfy all the demands. Okay, so is a problem statement clear here? Hopefully it is clear, right? So let's say, how do we formulate this as an optimization problem? Right? Actually, this is a Nobel Prize winning optimization problem originally proposed by Computational. So here, let's first talk about very naive formulation of this problem. So let's define some binary variables yk. So yk is 1 if the master row k is cut, right? So the master row has length 100 in the previous problem. And 0 if the master row k is not cut. So zik is an integer variable that says the number of rows with wi cut on the master row k, right? So for example, in this particular case, the ik for width 25 equals to 4, right? You can get 4 rows of width 25, right? So that's an integer number we have. Okay, so now the objective is to minimize the number of rows you use, right? Remember, ik is 1, that means the row is used, otherwise it's not used. If you minimize the number of rows, you just sum all of them up. And the constraints include 2 things, right? First, if you need to satisfy the demand, right? So recall that zik means the number of rows for width I on a given row. So you sum over all the rows you cut, that they have to be greater than or equal to the demand for the width I, right? So here, let's say the demand is 7, 5, and 3, then you sum them up, then you should be greater than or equal to their respective demands. And the last constraint is we cannot cut more than the available material, right? This is very straightforward. With length of 25, you can only cut 4. You cannot cut more, right? So that's why you have this constraint. You sum over wi times zik. They have to be less than or equal to the total length if this master row is cut, right? So if the master row is not cut, then yik is 0. Then all the zik will be 0, right? This w is like a big M parameter here. Okay. Yeah, so that's a formulation, a very naive formulation. Is this formulation clear here? Right. Yeah. And zik have to be integer variables as well. So maybe before I talk about the downside of this formulation, let me ask you guys first. What do you think about this formulation? Are there any issues with this formulation? Would this be computationally efficient? What do you see are the issues, right? So you learned about some of the theories related to formulating good integer programming models, right? This is an integer programming model. I can tell you that computationally, this formulation is very poor. Right? It doesn't scale very well with respect to the number of width and the number of rows. Right? What do you see? Takes more iteration. Why do you see that? What are the properties of this problem that make it take a lot of branch and bound nodes to solve? Or maybe anyone else have some thoughts here? Well, first of all, you can observe that the problem has a lot of symmetry here, right? Because each of the row is identical, right? You don't really care about those, which row you select here, right? So yk just decide whether a row is cut or not, right? If only 10 of the 20 rows are cut, there's a lot of symmetry, right? You can choose 10 out of 20 rows, right? So there are different ways of choosing it. It's a symmetry issue. And the other thing is the big M parameter, right? You have those, all those constraints are essentially some sort of big M constraints, right? So usually with big M constraint, it has very poor linear programming relaxation. Okay, so that's just a repetition of this formulation here. Yeah, so people have ran some computational experiments, and we find out that this formulation has very poor computational performance. One is because of the weak LP relaxation. The other is this highly symmetric and degenerate solution. Right? So once you find a solution of this problem by symmetry, you can always find it. Just switch the 2 paper rows, and then you can find maybe they were cut in the same way, right? You can find out for different types of width, you can get them in different ways, right? And maybe for 2 different paper rows, they are cut in the same way, right? And then if you switch these 2 rows, you get the same solution. So now the question is, how do we break symmetry? And or in other words, is there an alternative formulation? So we will show a formulation that we will introduce that is much better than the current formulation. Yes?
I'm sorry, does this have a weak LP relaxation?
Yeah, it's because of the big M issue, right? So you have a binary variable multiply a very large parameter. Okay. Usually if you plot this region, it has very weak LP relaxation.
But is the big M parameter in this case not tight? I guess would it?
Yeah, it is tight, but usually you think about this maybe facility location problem. Right? You have a big M, which is the number of facilities you have. Right? It is tight, but it's still that formulation can be very, very weak. Right?
Okay.
Yeah, it's just the nature of this formulation, not really whether you pick a tight big M or not.
Okay.
Okay. Yeah. Any other questions here? Okay. So we will show a different formulation called set covering formulation. So it's proposed by Gilmore and Gomery in 1961. So the key observation of the set covering formulation is the following. So if you observe, you can try to solve some instances, and then they find out the optimal solution only uses a few of all the possible cutting patterns. What do we mean by cutting patterns? Right? Here's what we mean. Right? So here you have a master paper roll with length 100. And there are different widths you want to get at the end. The demands are for these 3 different widths. Right? By cutting pattern, what we mean is the following. So for example, each of these columns is a cutting pattern. Right? So the first pattern will get you 4 of the 25 inches paper rolls, right? And then you get 0 for the 35 inches, get 0 for the 40 inches. In the second pattern, you get 1 of those 25 inches and then 2 of the 35 inches, right? That's the second. You can cut, 100 inches in this way. And the third cutting pattern is the following. You get 1 25 inches, 1 35 inches, and 1 40 inches. You can find those, cutting patterns from this figure here, right? The first one, you just uniformly cut this paper roll into 25 inches, and in the second one, you get 1 25 inches, 1 35, and 2 35 inches, and in the third, you do it differently, right? So people have found out that in the optimal solution of this problem, all the patterns that were used are these only 3 cutting patterns, right? Of course, they calculated they are in total 15 different ways of cutting those 100-inch paper rolls, right? Of course, intuitively you can find out those 3 patterns seem to be good, right? Quote good, in the sense that they are not wasting too many trim loss, right? These 2 are like the perfect cut. This one, it just wastes probably 5 inches of the paper roll. So those are the, let's say, quote, good patterns, right? So if you formulate the problem in terms of the patterns, we can get something called a set covering formulation, right? So let's say for the sake of the argument, we are only going to use these 3 patterns, right? And then we define an integer variable xp. It represents the number of master rows to be cut with pattern p, right? So that means, so if you look at this case, here I'm talking about, I'm going to use this cut pattern once, and then this cut pattern once, and then this cut pattern 3 times. So the x variable is representing how many times you are going to use this cutting pattern, right? And with this representation, the formulation will be changed, right? So why it's called a set covering problem? The reason is that you need to cover all the demands with the patterns you are going to use. So here we have 3 patterns, right? And we are going to determine how many times we are going to use each pattern, right? So we use x1 variable to represent how many times we are going to use cut pattern 1, right? Remember in cut pattern 1, we get 4 of the 25 inches width, right? And we get 0 of the 35 inches and then 0 of the 40 inches width, right? And then the coefficients of each of these variables represent the number of rows you get for each width, right? And then you want to cover the demand by saying that the first row represents the number of 25-inch width I'm going to produce by using these 3 patterns, right? Then if you add them up, they have to be greater than or equal to 7. Okay. And for the second row, we are talking about width 35, right? So only the second and the third pattern will produce width 35. So the second pattern will produce 2 of the width 35. So you do 2 times the x2 and 1 plus 1 times the x3. They have to be greater than or equal to 5. Okay. Any questions related to this form? Yes?
If you didn't know what the optimal patterns were, can you just add all possible patterns?
Yeah, so that's exactly the motivation of our algorithm, actually.
Okay.
So here we will just assume we know the optimal patterns. You can formulate it that way, right? Of course, if you don't know the optimal patterns, there will be an exponential number of patterns. You are not going to enumerate them, right? So how do you choose them in a very smart way? That's the motivation of our algorithm. But let's say if you know the optimal patterns, that this formulation makes sense. Any clarification questions related to this? Okay, yeah. And the objective here is to minimize the number of rows used, right? So recall that xp represents the number of rows you use for pattern p, right? And in total, you will use the summation over xp number of patterns. Okay, so as Jatni already alluded to, if you want to find the optimal cut, you need all the possible patterns, right? So let's have this very generic formulation with all the possible patterns, right? So here, recall that xp represents the number of rows you are going to cut using pattern p. And then let's define a capital P represent, all the possible feasible patterns for a given problem, right? And this a sub ip, it is a parameter, right? So this parameter represents the number of rows of width wi in a given pattern p, right? So what this AIP number is, they are, the numbers you have in this in this table, right? So the AIP would be those numbers here. For each of the pattern, how many of the given width you are able to get, right? So for the first pattern, the A1P equals to 4, then A2 equals to 0, and so forth. Right? That's a number we are talking about here, right? So we have this set cover formulation which says, if you have all the possible feasible patterns, then you sum them up. They have to be greater than or equal to the demand for a given width I, right? And then let's assume you have m different width you want to produce, right? In our problem, the different width are 25, 35 and 40. Right? That's a different width we have. And of course, if you consider using all the patterns, let's do a quick calculation how many feasible patterns are possible, right? So let's do a very rough estimate. Let's suppose J is an average number of cuts in a feasible pattern, right? Usually, let's say J is in the previous problem, J is a number like 3 or 4, right? So in each of the paper row, you can get 3 or 4 number of cuts in a feasible pattern. But then you have to choose from, all the possible width, which is m different width, right? You have to pick J out of the m. So it has a combinatorial growth, right? And then of course, you can estimate J just by taking the weighted average and so forth. But as you can imagine, as the number of width grows, right? If you have goods with 20 different widths, and each of the problem you are picking 10 out of the 20, this can grow very fast. So here, for a typical real-world problem, it says maybe you have m different orders of width. If you are just picking 10 out of the 50, you could have 10 billion feasible patterns in this particular problem, right? Okay, so that is definitely intractable, right? So we are solving the problem of symmetry and weak LP relaxation by introducing this set covering formulation, right? So I can tell you this formulation has very good LP relaxation, and it also avoids the symmetry issue, right? Because you are talking about the numbers of a given pattern, right? So that automatically solve the symmetry issue because you don't really care about which of the row you use this pattern, right? You are just considering the number of patterns that are using this particular pattern. But we have a new problem to solve, right? The number of patterns has a combinatorial growth. You are not going to have all the patterns in this particular formulation. So how do we solve this problem? That is the motivation of column generation algorithm. Right? No questions? No. Okay, so let's do some very quick analysis. How good this is model? This model is good because it has a very strong linear programming relaxation. I will show you in a second why it has very strong LP relaxation. And there are no symmetry issues as well, right? Because you are talking about the number of cuts you get for each pattern. But there are also computational challenges. If we explicitly list all the patterns, even if you don't talk about the CPU time, you could quickly run out of memory, right? We have 10 billion binary variables at least for each of the patterns, right? We cannot solve a problem of this size. But on the other hand, if we had the optimal patterns from the start, then we could terminate very fast, right? Because only the optimal patterns will be chosen. Then all the other patterns, you can just fix them as 0, right? You can get rid of all the other patterns and only decide how many you are going to cut from those optimal patterns, right? And these optimal patterns is usually very small. For example, in the previous toy problem, in total there are 15 feasible patterns, but the optimal patterns are only 3, okay? And for a bigger problem, you can see a bigger difference between the possible number of patterns and the optimal patterns. Okay, so now the question becomes, how do we really develop a method to find those useful patterns? Okay, so let's first analyze the property of the linear programming relaxation of this problem, right? Recall that in the original problem, all the x are integer variables, right? So now we consider x to be greater than or equal to 0. They are all relaxed as continuous variables. And I will also show you very quickly that this problem has very tight linear programming relaxation. Okay, so for simplicity, we just assume all the rows you produced exactly satisfy the demand instead of greater than or equal to, right? The reason we want to do that is because we want to write it in as a standard form of linear programming problem, right? You can write it as greater than or equal to 0 as well. But in practice, usually you exactly get the number of rows you need. The reason is because we are not restricting x to be an integer variable, right? It's a continuous variable, so you can get a fractional number of rows when you are talking about a continuous relaxation. Okay, just for simplicity, we will just assume we have a standard form of linear programming problem, right? All the x are greater than or equal to 0, and the rest of the constraints are some equality constraint. It assumes that if you produce xp of a pattern P, you will exactly satisfy the demand Ni. Okay. Yeah. So just to refresh your memories, right? We are using all the feasible patterns. The number of feasible patterns can be very large. That means the number of continuous variables in this linear programming is very large, right? But the number of equality constraints is very small, right? M means different types of width you need, right? You could perhaps only need 10 different widths, right? So M equal. You can think about M as a very small number, but P can be 10 billion, right? So let's write down the numbers, then we can analyze it better. So let's say in practice, M can be 10, right? And the cardinality of P can be 10 billion, let's say 10 raised to the power of 10. Right? So this problem have very few constraints, but a lot of variables. Right? Okay, that's a property of this problem. Okay, so remember what we have talked about in linear programming, right? The optimal solution of a linear programming problem can always be obtained at a basic feasible solution. Right? So recall that in simplex method, you define something called basic variable, non-basic variable. Right? If you have a linear programming standard form, then for the basic variables, you choose the columns corresponding to the basic variable. That's called a basis matrix. Right? And you take the inverse of that basic matrix, multiply the right-hand side, you get the value of the basic variable. For the non-basic variables in linear programming problem, you set them as 0. Right? Okay. Then let's analyze this problem. Right? So at a basic feasible solution, out of the P inequality constraint, at least P minus M of them are active. Right? So we only have, let's use the numbers 10 and 10 billion here, right? We only have 10 equality constraints, right? And at a basic feasible solution, you need 10 billion constraints that are active, right? So in other words, in a basic feasible solution of this problem, most of those variable xp are 0, right? You can have at most 10 non-zero xp's in this problem, right? So in other words, in an optimal solution of this linear programming problem, you only need 10 patterns out of these 10 billion patterns to solve this linear programming problem, right? The challenge is just you need to find those 10 patterns that are optimal, right? Okay. So in other words, at most, M of those xp's are strictly greater than or equal to 0 in a basic feasible solution of this problem. All the rest of the patterns are not used in the optimal solution, right? And we need the columns AIP corresponding to these optimal patterns, right? Okay. And then the other final thing to show is that this problem has very good LP relaxation in the following sense. Think about the following. We get a fractional solution from this linear programming problem, right? So the xp's may not be an integer value, right? But if you round up all the xp's, it is a feasible solution to the original problem, right? Because you already have all the xp's will help you satisfy the demand, right? If you round all the xp's up, then of course they will satisfy the demand, right? So in other words, this LP relaxation at most differs from the original integer programming problem by n. Okay, so you have m xp's that are optimal here, right? So you are cutting out m xp's that are optimal, but those xp's might be fractional, right? They may not be an integer number of rows you cut. Let's say you round all of them up, since the original fractional number of rows already satisfy the demand. If you round them up, you will of course be able to satisfy the demand, right? But then there are only m of those xp, right? Say m equals to 10, right? You are only rounding 10 of the fractional numbers up, right? So after you do all the round up, you are just increasing the total number of paper rows by less than 10, right? So that's saying that, the optimal value of this linear programming relaxation at most differ from the original integer programming problem by m, right? So m can be a very small number. That can be, for example, 10, right? You have 10 different patterns, but not 10 different patterns, but 10 different orders of width. But the number of patterns can be large. Okay. Yeah. So that kind of gives you some intuition why this linear programming problem have good LP relaxation. Yes?
So how are we making sure that whatever bits we are cutting, that is within the total width range?
Total width range.
Let's say if our total master rule is of 100, and whatever bits we are cutting here in this formulation, they are within the 100.
Oh, okay. Yeah, that's a good point, right? So you calculate these AIP parameters a priori already, right? You are only going to add the feasible patterns into this problem. Okay, so that says these P are so-called feasible patterns, right? For example, if the length is 100, you are only going to get 4 of the 25 inches. Right? You will not add a column saying that you are adding 5 of those. So you kind of implicitly satisfy the constraints by adding only the feasible patterns, right? Yeah. Other questions here? Yeah. So now the next question is, how do we use an algorithm called column generation to generate the optimal patterns, right? The optimal patterns can be a very small number, then we will have a method of doing that. So the idea is the following. Before we go to the math, we will start with an initial subset of feasible patterns. Yes?
I'm sorry, this is just going back to the last time.
Yeah.
Doesn't that still have the problem of like space constraint? Because you still have 10 million constraints potentially, right?
10
Or would you
million.
not?
No, you don't have 10 million constraints, right? You only have 10 constraints here, right? So those constraints are saying that you have to satisfy the demand for the 25 inches, 30 inches, and so forth, right? So if you have 10 different types of demands, then you have 10 constraints here.
Okay.
Right, yeah.
Okay.
Right, so let's say if you go back to this toy problem, right? So the demands are for those 25 inches, 35, and 40, right?
Yeah.
And all the constraints are corresponding to the demand of different width, right? So for the demands of different width, you have only a single constraint.
Yeah.
That's all the constraints you have. If you have 10 of those, then that's 10 linear constraints you have, right? These columns, the number of columns here can be very large. I'm listing 3 columns. In practice, you can have 10 billion columns. Yeah.
Okay.
Right. Yeah.
But sorry, go ahead.
Yeah.
When you do it, I guess that's sort of what I was referring to.
Uh-huh.
Having like those 10 billion columns isn't an issue within LP relaxation.
Yeah, so you will start with, let's say, 10 columns, and then you gradually add the columns that are needed. So in practice, you will end up probably only have less than 100 columns.
Okay.
Then you can prove that those are the columns you need.
Okay.
Right? Yeah. So there are some ways using the argument of linear programming optimality conditions. If you have the optimal 10 columns, you can prove that those are the optimal 10 columns you need, then you are done.
Okay.
Right? No need to add all the rest of the 10 billion ones.
Yeah.
Okay. Yeah. You have a question, Ira?
I'm a bit confused. So is that equivalent of saying the number of optimal patterns are at most equal to the number of ends, like I?
Yeah. Yeah. So the number of optimal patterns is equal to the number of different width you have, right? That's because of the solution to the linear programming problem always is obtained at a basic feasible solution. Since you only have 10 constraints, then the number of non-zero basic variable is at most 10. Yeah, yes?
Suppose there is a situation when we are given 10 rows of 100 inch width,
Yeah.
but then there is a demand that I have to cut 11 rows of width 60 inches. So this thing is not feasible. So how do we include that in the formulation?
Yeah, so you did not include that explicitly, but this problem is giving you the minimum number of master rows you can get, right? So let's say if you only have 10 of those, you solve this problem, then you get 11, then you can claim this problem is infeasible, right? Yeah. So you are not explicitly accounting for the number of rows you have at the beginning. Okay. Yeah. Yeah, so as I said, there are only, let's say, 10 optimal patterns. How do we generate those 10 optimal patterns, right? So the idea of column generation is the following. You start with the initial subset of feasible patterns. Right? This initial subset can be very small. Right? I will tell you how to generate this initial subset. You can assume this, you have a subset of patterns which is equal to 10. And it is guaranteed to be feasible. I will show you real quick. Then you solve the LP relaxation for those feasible patterns. Then you get a solution to the LP, right? But now you need to check whether you should add more patterns into this LP, right? Since we are only including 10 patterns into the linear programming problem. So the way to check whether you need more patterns is a problem called the pricing problem in column generation, right? So we will talk about how the pricing problem works. That is the most critical step in a column generation method, right? And then the way to derive the pricing problem is dependent on the optimality condition of linear programming problem. Right? I will remind you what is the optimality condition of linear programming problem later. Okay, so now let's start with the first iteration of the method. You generate a very small subset of the feasible patterns. You can assume now I have the first iteration, P0, the cardinality of P0 equals to 10. Okay, so let's assume you have orders of 10 different widths. How do I generate the initial feasible patterns, right? So you can do the following, right? For each of the orders, right? I'm only going to use the whole master row to cut order of this particular size, right? So let's say if you have orders with 25 inches, 30 inches, and 40 inches, right? We have 3 patterns here. Then the initial pattern I'm going, not 3 patterns, we have 3 different widths here, right? Then the initial pattern I'm going to include will be the following. For this material with length 100, for P1, I'm only going to use the whole row to produce paper rolls of length 25, right? So you will get 4 of those, 4 times 25, that's my first pattern. Then the second one, I'm only going to use it to produce with 30 inches, right? So I will get 3 times 30. That's my second pattern. Then my third pattern, I'm going to produce 2 times 40, right? So if I have length 100 in total. In other words, I will generate some very naive patterns, right? Those are not very good patterns for sure, right? I'm just going to use the whole length to produce a certain order, right? But these 3 patterns will guarantee to be feasible, right? Because each of the orders are produced by one of the patterns, right? You may waste a lot of material, but you are guaranteed to cover all the demands, right? Okay. Yeah. So that's what we are going to do in the first iteration. Okay. And by solving this problem, you will definitely get a basic feasible solution to the original problem, right? You can just treat all the columns you haven't, all the patterns you haven't added as a non-basic variable, right? They may not be optimal to the original problem, but by solving this problem, you will get a basic feasible solution for sure to the original problem, right? So think about you are doing some sort of simplex method, right? You are just introducing a subset of the column. All the rest of the columns, you don't care about them. You set all those variables to be non-basic variables. Since you only include a subset of these patterns, then your basic variable have to be chosen from the patterns you have added, right? Okay. So now what we can do is that if we find out that the basic feasible solution of this reduced problem satisfy the optimality condition of the original problem, then you are done, right? Okay. So let's quickly recall what is the optimality condition of a linear programming problem. We did cover that in linear programming, right? Does anyone remember the optimality condition of a, let's say, how do you check if a basic feasible solution is optimal or not? Suppose I give you the basis of that matrix. What is the quantity you are going to check? Yeah, exactly right. You are going to check the reduced cost, right? So in other words, now I gave you a subset of the feasible patterns, right? And then you can check the reduced cost of all the variables that we haven't added to this problem. If all of their reduced costs are non-negative, then we are done. Right. Remember the reduced cost meaning that if you push one of the non-basic variable to basic variable, how much will the objective change, right? If the reduced cost is negative, that means you can still reduce the number of paper rows you get, right? If all the reduced costs are non-negative, then you basically show that you don't need to add all the rest of the patterns since they should stay as the non-basic variables. Yes?
Do you have to check over all possible patterns then?
Yeah, so we will show you how to do that.
Okay.
Okay, yeah. Yeah, so just to recall how to compute the reduced cost, right? So you can define some sort of a dual multiplier. Let's say B is the basis matrix, then the dual multiplier is CB transpose. Recall that B are the basic variables, CB transpose B inverse. Then for all the patterns that haven't been added, then their reduced cost is calculated as a CP minus this AP is a piece column transpose the dual variable we defined here, right? That's a definition of the reduced cost. If all the reduced costs are non-negative, then you are done, right? And here we have all the CP equals to 1, right? Because in the objective, the coefficients for all the XP are 1, right? Then basically you need to check whether the AP transpose Y are strictly greater than 1 for a given P or not, right? If that is the case, we have a column with a negative reduced cost, then we need to add it back, right? So how do we find the columns with a negative reduced cost, right? So actually we will show that it can be formulated as an integer programming problem. You don't enumerate all the possible columns. Okay. Yeah. So this is where the capacity constraint you asked come into play. How do you generate a column with potentially negative reduced cost, right? So recall that we are trying to minimize we are trying to find the column with the most negative reduced cost, right? Then that help you improve the objective. So in other words, if you want to find the minimum reduced cost, you are trying to maximize AP transpose Y, right? Okay. So in the objective, we have the maximization of A transpose Y, right? And AI is a column corresponding to a feasible pattern. Okay, so AI says, what is the number of given width you are going to produce in a particular pattern, right? And what is a feasible pattern? The feasible pattern have to satisfy this capacity constraint, right? It says the width of order I is Wi, and then the AI is the number of width I you are going to produce in this particular pattern. And the summation of these have to be less than equal to the width of this master paper row, right? That's where the capacity constraint comes into the play. And in the objective, recall that the coefficients in the objective are the dual variables in the master problem, right? Recall that here you are trying to maximize this term AP transpose Y. And Y is the dual variables you get from the master problem. Or you can think about this as the basis matrix inverse times CB. Okay. Yeah, this is the most important part. I want to spend more time to help people digest how it works, right? So let's go back a little bit, right? In the master problem, you solve the master problem with a subset of patterns, right? And then now the question you ask is, should I add more patterns to the master problem, right? Because the rest of the patterns, you are treating them as a non-basic variable now in the master problem, right? A naive way to do that is I'm going to enumerate all the other patterns and check their reduced cost, right? But then we can formulate this as an optimization problem, saying that I'm going to pick the patterns that have the minimum reduced cost at this particular iteration. So how do I find a pattern with a minimum reduced cost? Here's the formula for calculating the reduced cost, right? You have the coefficients in the objective, and by definition, you can revisit your linear programming notes. This is how the reduced costs are calculated, right? Now what I want is I want to find a column. So find the column AP that minimize the reduced cost, right? So how do you find a column that minimizes the reduced cost? Recall that all the columns represent feasible patterns, right? Each column represents a feasible pattern. What does feasible pattern mean? That means that the pattern have to satisfy this capacity constraint. Okay. And in the objective, I want to find a column that gives me the minimum reduced cost. It's equivalent to maximize the dual variable times the coefficients of the column, right? So in other words, by solving this integer programming problem, you will hit a column that gives you the minimum reduced cost, right? And if the column that gives you the minimum reduced cost still has a non-negative reduced cost, then you are done, right? You know that all the rest of the column cannot be added there. Essentially, you are solving this problem to check the optimality condition of a linear programming problem with 10 billion variables, right? So just by solving this integer programming problem. Okay. Is this part clear? You have questions? Okay, yeah. And then another way to interpret the pricing problem is the following. If you treat you think about in the dual of the master problem, instead of finding the problem with the minimum reduced cost, you are essentially finding the so-called most violated constraints of the dual problem. Right? So the dual problem specifies all the reduced costs should be non-negative, right? That is equivalent to saying that, in the dual problem, do you have some violated constraints, right? The dual will specify all the reduced costs should be non-negative. And if you check this problem, this is essentially a knapsack problem with a single knapsack, right? And it can be solved quite efficiently. One of the algorithms to solve knapsack is to use dynamic programming. Maybe some of you guys have taken a course in algorithm. You don't need an integer programming solver to solve knapsack problem. You can use a so-called dynamic programming method to solve this knapsack problem really quickly. Okay. Yeah. And the application of column generation is not restricted to cutting stock problem, right? And there are a lot of practical applications nowadays that are solved with column generation and similar method, like vehicle routing problem, right? You are assigning those packages to different vehicles, and then they will deliver those packages to different customers, right? And then like aircraft routing problem, right? How do you, if you fly, the aircraft is flying through different airports on a daily basis, right? So you can all formulate those problems as a set covering problem, just like in the cutting stock problem, right? A lot of those aircraft are identical aircraft, right? You don't really care about, which aircraft you assign to which route. You only need to make sure that those routes will cover all the passengers you need. right? And similarly for crew scheduling, the airline companies are solving crew scheduling problem all the time, right? You have the crew that can serve different legs of those airplanes, right? Those are all solved with column generation and similar methods. Okay. Yeah, so now let's talk about something else called Dantzig Wolfe decomposition. If you understand column generation, Dantzig Wolfe decomposition is just a special case of column generation where the subproblem is a linear programming problem. Okay. So here, let's assume we have a problem of this particular structure. We have two sets of variables, x1 and x2. You can think about both x1 and x2 are in Rn, for example, right? So you have the objective related to x1 and x2. And you have three sets of constraints. The first set of constraints involve both x1 and x2, okay? And the second set of constraints only involve x1 variables. And the third only involve x2 variables. Right? It is a LP with a special structure. Right? So typically people call this type of linear programming problem as problem with so-called complicating constraints. Right? So as you can imagine, if you get rid of these constraints, then the rest of the problem is decomposable. Right? You can solve two LP separately because this set of constraints only involve the x1 variables. This set of constraints only involve the x2 variables. Right? So that's why it's called complicating constraint. Remember in Bender's decomposition, we have something called complicating variables. Right? If you fix the first stage variables, then the rest of the problem is decomposable by scenario. Here is like we have some complicating constraints. If you remove some constraints, then the rest of the problem is easy. Yeah. Okay, so like in Bender's decomposition, we first show a Bender's reformulation before we introduce the Bender's algorithm. Here what we will do is that we will first introduce so-called Dantzig Wolfe reformulation using the Minkowski-Weld theorem, right? So that's why I said Minkowski-Weld is one of the most important theorems you should remember in linear programming. Okay, so let's consider a problem like this, right? You have the complicating constraint, you don't have any choice but to keep them there, right? And then the rest of the constraints are decomposable, right? X is in a set P1. Let's assume P1 is just the F1 times X1 equals to B1 and X1 greater than or equal to 0. And for X equals to belongs to P2, you have another set of constraints, right? Those two sets of constraints are separable. Right. Okay, so now we realize that each of these PI sets are polyhedral sets, right? And according to Minkowski-Weld, the X that are in these polyhedral sets can be represented as a convex combination of extreme points and the conic combination of extreme rays, right? Yes, hopefully people still remember this theorem here. Right? So that's what it says, right? If you have x1 that belongs to the polyhedral set P1, then it can be represented as, so here the first part is a convex combination of extreme points where you use xj to denote the jth extreme points, right? And the wk are the sets of extreme rays, right? So you are using this theta I times wi as the conic combination of extreme rays. Okay, so here I did nothing but to restate the Minkowski-Weld theorem for two polyhedral sets, right? For each of the polyhedral sets, you can represent the xij as a convex combination of extreme points and a conic combination of its extreme rays, right? And for different sets P1 and P2, you will have their corresponding extreme points and extreme rays, right? Then you can do it separately. Okay. So let's use this, right? Then this is what is called a Dantzig Wolfe master problem formulation. Okay. So this thing looks very congested, but it's really simple here, right? So basically what we did is that we will replace x1 and its constraints p1 by the Minkowski-Well representation. And then we will replace x2 by its Minkowski-Well representation, right? So remember the original constraint is the follows. We have the original constraint is d1 x1 plus d2 x2 equals to b0, and we have x1 is in p1, x2 is in p2, right? That's the original constraints we have. And now we are going to replace x1 by, here is the convex combination of the extreme points of x1 and the conic combination of, so the W are the extreme rays of x1. Right? And similarly for x2, you are replacing it by the convex combination of x2's extreme points and the conic combination of x2's extreme rays. Right? So we did nothing but a reformulation. Right? Okay. And of course, you just replace the x1 and x2 correspondingly in the objective. Okay. So now let me ask you guys the following question. What are the variables in this problem here? What variables are we optimizing here? Yeah, exactly right. So you no longer have x1 and x2 anymore. You are replacing x1 and x2 with a convex combination and a conic combination, right? What you are deciding is what are the weights for this convex combination and conic combination, right? So all the variables in this master problem are the lambda 1, lambda 2, and theta 1, theta 2 here. That's what you are optimizing in this problem instead of x1 and x2. Yes.
Are those not fixed though by P1 and P2? I guess like you can't.
Yeah. So you can think about the P1 and P2 are something like a polyhedral set. This is P1, right? And then you have all the extreme points. You call it x1, x2, x3, and so forth, right? And all the points in P1 are a convex combination of those extreme points, right? So if you write x as a convex combination of this extreme point, it's essentially saying like for different weights for those extreme points, you are going to hit a different x.
Can you explain that?
Yeah. So yeah. So when you say so let's say yeah. So the following two statements are equivalent, right? If you see x1 is in P1. This is equivalent to saying that you have x1 such that x1 is a convex combination of the extreme points in this, let's say x1, we are using j, no, x1j, lambda j. Lambda j greater than or equal to 0. So these two sets are equivalent, right? So if you see x1 is in the set, polyhedral set P1, it's essentially saying that x1 can be represented as a convex combination of those 6 extreme points representing this polyhedral, right? And now you kind of, if you replace x1, anytime x1 appears in the original formula. So for example, x1 appears here, right? Then you just replace x1 by this bunch of stuff, right? Then x1 will automatically satisfy constraints x1 is in P1 because you are representing x1 as a convex combination of extreme points, right? And then the variables that are left to be determined are those lambda variable, right? You don't know how you are going to do the convex combination, right? So that's why I say in this optimization problem, the things that are left to be optimized are the lambda and theta variables. Okay. Yeah. So that's what we do here, right? So the nice thing here is that we are significantly reducing the number of constraints, right? We only have the original constraints, which are m. Let's say the original constraint are m0 number of constraints. Then we are adding, two more constraints. The lambdas, sum of lambda has to be equal to 1, right? And all the constraints in those P1 and P2 are gone, right? But we pay a very heavy cost by enumerating all the extreme rays and extreme points, right? There could be exponential number of extreme rays and extreme points in this Dantzig Wolfe reformulation, right? And then how we are going to pick those good extreme rays and extreme points here? Yeah, exactly, right. We already talked about how to pick those active columns, right? So here, recall that if you think about, what are the columns in this problem? All the columns in this problem correspond to the extreme rays and extreme points. Right? So for each of the, I said, for each of the lambda variable here, you are using, you have a lambda times its corresponding extreme points, right? So whenever you introduce a new extreme points, you introduce a lambda variable, right? In other words, you introduce a column in this problem, right? Then how do we generate those optimal extreme rays and extreme points, right? This is very similar to the cutting stock problem in the sense that the number of active extreme points and extreme rays are very small because this problem have very few constraints. Right? It only have m+2 equality constraint. That means the number of non-basic variables in this problem is at most m+2. Right? So the number of basic variables is very small. Okay, so that's basically a summary of what I said. The original problem have this many constraints, but we are reducing it to m0 plus 2 constraints. But the decision variables in the master problem can be very large because you have an exponential number of extreme points and extreme rays, right? It's similar to Bender's decomposition in some sense, right? If you add all the possible Bender's cuts, you are enumerating all the extreme points and extreme rays. And in Bender's decomposition, what you do is that just start with a small number of cuts, and then you check which cuts are violated by solving the subproblem, right? And in Dantzig Wolfe decomposition is very similar. It's like you start with a very small number of columns, and you check by solving a pricing problem which of the columns give you a negative reduced cost. Then you add this column back, right? So there are some kind of duality between Dantzig Wolfe decomposition and Bender's decomposition, right? So Bender's decomposition is to check what are the violated constraints to add. This is to check what are the violated columns that will give you a negative reduced cost, right? So there are some sort of duality between these two problems. Okay, and the other observation is that at a basic feasible solution, I already said there can be at most m0 plus 2 non-basic variables, and most of those lambda and theta are 0, so you don't need all of them. Okay, so we will use column generation to generate the columns corresponding to the basic variables. Yeah, so essentially you are going to do the same thing as I told you in the column generation methods. We will start with a master problem with a small set of extreme points and extreme rays. How to get a feasible one that could be application dependent, right? You probably for your application, you know how to get a feasible solution to start with. And now we consider a basic matrix. Of course, the optimal solution is obtained at a basic matrix. You can calculate the dual vector, and the dual vectors have M0 plus 2 components, right? The first, you call it Q, that's for the first M0 equality constraints, and then the last 2 components, you call it R1, R2, okay? And then we need to calculate the reduced cost for the jth variables here. Right. So to get the reduced cost for the jth variable, recall that all those variables are generated from the polyhedral set P1 and P2. Right. So you are going to generate a column from the polyhedral set P1 and P2, and you can check the details here with regard to the original formulation. But this will give you the column with a minimum reduced cost, right? So you can just double check if this is this problem is trying to solve the problem that give you the minimum reduced cost here, right? Yeah. So what we are going to do next is we solve this linear programming problem. If this optimal cost is minus infinity, that means you can find a column whose reduced cost is unbounded. Then that means you find an extreme ray that give you a reduced cost that is negative. Then what you can do is you add that extreme ray back to the Dantzig Wolfe master problem. And if the optimal cost is finite and it gives you a negative reduced cost, then you will find an extreme point that gives you a negative reduced cost. Then you add an extreme point as a column back into the master problem. On the other hand, if the optimal cost is finite and then you check the reduced cost is non-negative already, then that is a certificate that the column you have added is enough to prove optimality. Right? It's very similar to the cutting stock problem, except that you may have an unbounded extreme ray here. Yeah.
So just to be clear, the columns that you can add in this case can be either extreme rays or extreme points?
Yeah.
Okay.
Okay, yeah. So for the sake of the argument, if you want to try implementing this, you may first assume you have a bounded subproblem, right? Then you can only get extreme point, right? So for most of the practical applications, you won't need to deal with extreme rays. Okay. Yeah, so let's just repeat the procedure, right? You start with a basic feasible solution to the master problem. Then you solve 2 subproblems for P1 and P2. If both problems yield non-negative reduced cost, then you prove that a current solution is already optimal. Otherwise, you will either generate an extreme ray or extreme points that give you a negative reduced cost. Then you can add a column back to the master problem and resolve the master problem. Then you will get a different optimal basis, and then you solve the subproblem to check optimality, and you keep iterating.
Do you add, I guess, an extreme point, extreme ray for each subproblem? So I guess you're
Yeah.
iteration.
Yeah,
Okay.
exactly. Yeah. There might be some cases where one subproblem is optimal, the other is not, right? Then in that case, you only add one of those. Yeah. Okay, so you keep repeating this procedure until the pricing problem always give you a non-negative reduced cost, and then you converge. Yeah, and of course, in practical applications, you might have multiple blocks, right? Of course, if you only have 2 blocks, you don't get that much parallelism, right? So if you have multiple blocks, you can run all those pricing problems in parallel, right? So in each of the subproblem, you are generating an extreme point from the subproblem P sub I. Yeah. And in a number of practical applications, you will find this type of structure. Right? Then you can apply Dantzig Wolfe decomposition to solve this type of problem. So to summarize, Dantzig Wolfe decomposition is just a special case of column generation. Right? The philosophy of column generation is the following: you have a master problem, but the master problem only have very few constraints, but a huge number of variables, right? You know most of those variables are useless. So you are going to solve a pricing problem to find those active variable, quote, active variable, or the variables that should be in the basis. Usually the active variables are very few, so you can take a few iterations to converge if your initial starting point is good, right? And usually those set covering formulation is very tight, give you a very tight LP relaxation. You don't even need to do much branch and bound to converge. Okay. Yeah. Any final questions here? Okay, great.